Right, welcome everybody to this week's GOCC. Before we get started with our awesome talk, I just wanted to remind everybody of our community statement, which you can access on the GOCC website. And so we have three guiding principles. The first one is that we are all learning. The second one is everyone has something to contribute. And with that, if you have questions for the speaker, Galen and Alex and I will be monitoring the chat, or you can unmute yourself and ask a question if you find an appropriate time. It's kind of weird during Zoom, but feel free to ask questions, and questions are encouraged. And the last one is no one has all the answers, not even the speaker, surprisingly. So this is a learning environment, and hopefully it is a welcoming environment. And yeah, and so let's get started. This week, I have the pleasure of introducing Lei Shui, who's at the University of Washington, is one of Isabella Novik's student, if I remember that right, yeah. So Lei and I met last summer in Paris when we were doing the geometric and algebraic combinatoric summer school. And we're fortunate enough to have her here today. And she'll be talking to us about a proof of Grünbaum's lower bound conjecture on general polytopes. So everybody, please welcome Lei.
Right, thank you for introducing me. I'm happy to speak here. And today I'm indeed going to talk about a lower bound conjecture made by Greenbaum on general polytopes. Let's get started. So let me talk a little bit about the structure of this talk. We're gonna start, I'm gonna define everything I need. As you can already see, the first definition is a polytope. So starting from that, after the definitions, we can state the conjecture and talk about the proof of the conjecture, and that will be the first half of this talk. For the second half, we're gonna deal with some cases when equality holds. Okay, and feel free to interrupt and ask any questions if you have. And sometimes if you feel like the screen is getting frozen, I think it happens sometimes if you feel like I'm already in the next slides, but the screen hasn't changed, just let me know. Okay, so what is a polytope? If you just pick a finite set of points in RD and look at the convex hull, that's called a polytope. And if you add one more restriction, you ask that finite set to be affine independent, then you get a simplex. I try to include as many pictures as I can, but I can only draw up to 3D. So there'll be many easy examples. So the green one is a polytope, and the blue one is moreover a simplex. They're both in 3 dimensions. And then a face of a polytope is what you get when you intersect the polytope with a supporting hyperplane, which is something like this. So a supporting hyperplane is a hyperplane that barely touches the polytope. So it has an intersection with the polytope, but not in the interior. Okay, and you look at this intersection, so this pentagon is a face. It's actually a 2-dimensional face. Here's another example. This is a vertex. This vertex is also a face. It's 0-dimensional. So a k-dimensional face is called a K-face. And depending on what that K is, we'll give the faces different names, starting from vertices, edges, and if you're dealing with a D-dimensional polytope, then the polytope itself is the unique D face. And D-1 faces are called facets. Those are the maximal proper face. And we also have a vector that can sort of keep records of faces of different dimensions. That's the face vector, so-called F vector. And here's an example. So this green polytope that we have seen has 10 vertices, 20 edges, and 7 two faces. Okay. And we also need a definition called, really, I got that wrong? Okay, let's come back. I think you're right. Okay, nice cut. But 7 two faces? 1, 2, 3, 4, 5. Okay, yeah, that should be right. Thanks. Okay, so we also need to define a vertex figure. So a vertex figure of a polytope at a chosen vertex is what you get by, first of all, sliding in a hyperplane that can separate the chosen vertex from the rest. And you just look at the intersection. And that's the vertex figure at that vertex, denoted as P mod B. This is also quotient polytope. And the reason why we like vertex figures is that is because of this following nice proposition. There's a nice bijection between the following two sets. K faces of P that contains V, and the set of all K minus 1 faces in the vertex figure. And I mean, the bijection is very natural. For example, if you start from a 2 face, let K be 2, then this face is a 2 face of P containing V, which is corresponding to, okay, now you intersect it with this hyperplane, and you get this edge, which is an edge here. It's of dimension 1 lower, and it's a bijection. Okay. Okay, now we can state the conjecture. So here's the main question. If I fix the dimension of a polytope to D, and I also fix the number of vertices to N, then one can ask, what is the minimum possible number of I faces of such polytope? And moreover, you can ask, is there a polytope that has the component-wise minimal F vector? So basically, each Fi of that polytope is the minimum possible Fi. Okay. Why we're asking that question? Because we know the answer if we restrict to simplicial polytopes, right? And that's pretty famous as the lower bound theorem, proven by Barnett, which says that stacked polytopes have component-wise minimal F vectors. If we restrict ourselves to simplicial ones. And we know a lot more. We know the other side too. So we also know component-wise maximal F vectors exist. And that's the upper bound theorem proven by Mike Volin. The polytopes achieving the component-wise maximal F vectors are called cyclic polytopes. We're not going to define either of these today. And for simplicial polytopes, we even know more. There's G theorem proven by Bilera and Lee and Stanley, which gives a full characterization of possible F vectors.
I have one question. So when you talk about the component-wise minimal F vectors, you might have said this before, but does that mean that every F vector is minimized, or is it that they're minimized for the smaller?
What do you mean by every F vector?
Like I mean, for every I, is Fi minimized simultaneously, or does it mean
yes.
that? Okay. And this, because it's not obvious that you would get them all simultaneously minimized, but that ends up being true in this case.
Yes.
Okay, cool.
Yes, I agree. It sounds to be, yeah, it sounds impossible, but yeah, for this conjecture, in our conditions, it's true. Okay, actually the upper bound theorem can be, actually also works for general polytopes, but not the lower bound. So our question on the lower bound still holds, okay, for general polytopes. And actually we know very little. We knew very little. So for example, if this N number of vertices is strictly bigger than 2D, then we don't even have a conjecture to work with. The conjecture only exists when the vertex number is at most 2 times the dimension of the polytope. And that's Grünbaum's conjecture in 1967. And here's his conjecture. So the vertex number is at most 2D, so we say we have D plus S vertices where S is at most D. And then Grünbaum conjectures that the number of K faces of such polytope is at least this expression here. And since we're working with this alternative sum of binomial coefficients through this talk, let's give it a name. I mean, it's also the name Grünbaum gave it to that. Call it phi k d plus s comma d. The first component in the parentheses denotes the vertex number, and the second one denotes the dimension. Okay. And here's some previous results. So Greenbaum himself proved the case when s equals 2, 3, and 4. The case when s equals 1 is trivial because there's only one D polytope with exactly D plus 1 vertices. That's the simplex, and it trivially satisfies this formula. And the following three others, forgive me if I got the pronunciation wrong. Pineda, Villa, Vicencio, Yugon, and Yost proved last year for the case when k equals 1. So basically, that's the case for the edge numbers. And this year, what we're able to show is that the conjecture holds for all dimension D and all k. Okay. Any questions so far? Okay.
Yeah, can you give some intuition about the terms? So it's clear in the conjecture that the D plus 1 choose k plus 1 is coming from simplex. But what are we thinking when we're thinking that this is the number of k phases we're going to get at minimal? What is that, the other two terms representing there?
Okay. Is there a concrete polytope that realizes the lower bound? Yes. Okay. So I don't find a good reasoning like to tell you the second term counts the following category of phases, and there's overlapping, so we subtract the third term. Basically, Grünbaum had a group of polytope, which is the candidate, and that polytope will achieve this phi k for every k, and we just need to show that it is indeed the lower bound that we're looking for. Okay, we're going to talk about that class of polytopes in the second part. Okay, thank you. Thank you for the questions. Okay, so before getting to the proof of the theorem, we're going to prove this following key proposition first, which is hopefully simple, but turns out to be very useful in the proof. So for the key proposition, we don't really care about the number of vertices of our polytope. Let's just assume that the dimension is D. And I want to pick a random set of vertices of P of size M. And I want to show that the number of K faces of P that contains at least one vertex from that set is at least this number on the right-hand side. Okay. And we're going to prove it in 2 steps. So first of all, in step 1, we're going to construct the following sequence of faces of length M. And for each I, Fi is going to satisfy all 3 conditions here. So for each I, the dimension of Fi should be D plus 1 minus I. So for example, F1 should have dimension D, which means F1 is just P. And F2 is a facet, and the dimension is decreasing 1 by 1. And for each Fi, I needed to contain the vertex Vi, but not any Vj that comes before. Okay, and we're gonna construct such a sequence by induction. So the conditions are still on the board. On M, if M is 1, there's nothing we need to do. Just pick F1 as P. If M is 2, then F2 need to be a facet that contains V2, but not V1, and we can always pick such a facet. And then we apply inductive hypothesis on this set of vertices of size m minus 1 to get F1 all the way to Fm minus 1, satisfying all 3 conditions. But we can also apply the same hypothesis on this slightly different set of vertices. And that will give us a D plus 2 minus M dimensional face, call it G, that will contain VM, the other direction, but not any previous ones, right? By the inductive hypothesis. So if this G, if Vm minus 1 is also outside of this face G, then we're probably done. But even if G contains Vm minus 1, it's still okay because this face G has dimension 1 higher than Fm we're looking for. So we can always find the facet of G that contains Vm, but not Vm minus 1. And that's our Fm. That's how we construct this sequence. And then we start counting. So we're going to count the number of all k faces of P that contain some Vi in the following way. So each time we'll only count the number of k faces containing Vi, but not any previous Vj's. But that's bounded by the number of, the union of k faces of Fi that contains Vi, according to our construction. And since this union is disjoint, I can just substitute it with a summation. And now we can use this nice bijection we learned about vertex figure. We know that there's a bijection between these two sets. And then Fi mod Vi is of dimension D minus I. And we're counting the number of k minus 1 faces in it. And that's going to be bounded from below by the number of k minus 1 faces of a simplex of the same dimension. And we're done. Is there any question in this key proposition? Okay. Anyway, I can provide, again, low dimensional example. So let's say we pick V1, V2, V3 from this. In this step, can you use Grünbaum's lower bound? What do you mean by Grünbaum's lower bound? Is that what we're going to prove?
Yeah, so maybe you use like induction on the dimension or something like that instead. So then you get a sharper bound here, perhaps. Oh, that's not possible, I guess. Never mind.
I'm not sure if I understand the question. So Grünbaum's lower bound is what we're going to show, and this key proposition is one step of it.
Yeah, maybe you can use induction, but because it's like a lower dimensional phase. But it doesn't matter because you can't get a anything sharper than Grünbaum anyway because it's maximal, right? So, or it's like it's sharp. So never mind. That was a stupid question. But okay, thanks.
All right, thank you. Thank you. Just answered your own question, but thanks. Okay, back to this example. So let's say we pick V1, V2, V3, and let's just try to find F1, F2, F3. There's probably no unique choice. It doesn't have to be unique. So F1 has no choice, it has to be P. And then for F2, we need a facet containing V2, but not V1. And for this example, there's a unique choice, right? Which is this sort of gray triangle. And for V3, we need to find an edge containing V3, but not V1, V2. And here we have two choices, and we can pick either one. And and the order actually matters because if you swap, for example, V1 and V3, then when you look at the vertex figure, F1 mod V1, instead of triangle, in that case, will be a rectangle. In that case, you will count more. The number you get will be strictly bigger than this number. So in many cases, this bond will be really bad. You're going to miss a lot of faces. Okay, and before we move to the proof of this theorem, we're going to use three useful but hopefully straightforward formulas about Vk. Oh, Thank you for liking the figures. Okay, let me remind you what phi k is. And basically the following three formulas either is straightforward by plugging in some numbers or is some application of the Pascal triangles. Okay, the first one you get it by plugging s equals 1. And for the second one, I think it's rather famous identity related to binomial coefficients. And the third one is, I think you use the first formula and Pascal's triangle. So for the first one, you start with this phi k d plus s, and here the dimension is 1 lower than we need, and you add these two binomial coefficients, and eventually you get something with phi k d plus s, and the dimension is higher, 1 higher. And that will be useful in our induction later. Okay, now we can prove it. So the proof will be an induction on S, where F0 is D plus S. So the base case is done. S equals 1, P is just the simplex. Actually, we know more, right? Grünbaum himself proved it for S equals 2 to the 4. So we know the first several cases. And for the inductive step, here's what we need to show. So assuming that the statement holds for all pairs D prime comma S prime, such that S prime is strictly smaller than S and weakly smaller than D prime, we need to show it for the pair DS. Okay, and here's what we're gonna do. We start by picking a facet F such that there exists at least 2 vertices outside of it. And that's all we need. Let's say there are M vertices outside of it, call the outside vertices V1 through Vm. And now keep the picture on the board. And then we can just immediately start counting. The set of K faces of P can be split naturally in the following 2 categories. Either it's a K face of F, or it's going to contain some outside VIs. Okay. And then if it's in F, by our choice of F, you use inductive hypothesis, and if it contains some VI, we use our key proposition. And that's basically it. So the red part comes from inductive hypothesis, and the blue part comes from the key proposition. And then you do some simple rearrangement using the formulas I mentioned. I'm really not hiding anything here, but for more details, you can check the paper. So you end up with phi k d plus s comma d, which is what we want, plus a summation. Oh, thank you, Sarah. Plus some summation of the difference between 2 binomial coefficients. But since s is always greater or equal to m, it's always non-negative. And the proof is done, or almost done, because remember that at first we picked a facet that with at least 2 vertices outside of it. We still need to deal with a case when it's impossible to do that, but that will mean that for any facet, there exists exactly 1 vertex out of it. Okay, that will mean that P is a pyramid over each of its facet. And the only possibility is that P is a simplex. And that's the first case. Okay, now we're officially done. Is there any question with this proof? Oh, thank you, Mark. Okay. If there's no question, we can move to the second part, which is the treatment of equality. Okay. And this probably can answer a question, why that lower bound? Why that expression? Okay, so here's the question when we're dealing with equality cases. So which polytope will satisfy this for all Ks? Okay. And are there other polytopes satisfying this equality for some Ks, but probably not all of them? Okay, So we're going to deal with very specific examples of polytope. So let me just define more things, just by pictures. We sort of already talked about pyramid, but officially pyramid is what you get by starting from a lower dimensional, like d-1 dimensional polytope, and you add a new vertex to make it dimensional. And you can do this operation multiple times to get a multifold pyramid. If you apply it k times, it's called k-fold. You can also define bipyramid. There are probably many ways to define that, but since we just defined pyramid, you can think of it as two identical pyramids glued on the basis, and you look at the union.
So can you explain again what a k-fold pyramid is? So for a pyramid, do you have to glue the point to every point of the polytope? Or I guess attach it with an edge, I should say, not glue it?
Yeah.
And then is k-fold that at first I thought you were saying that it was like a bipyramid, but where bipyramid would be twofold, but
no. So, okay, so let's go back to the previous slide. Let's forget about bipyramid. So here we start from a two-dimensional polytope, and by adding this purple apex, we made it three-dimensional, and that's one-fold pyramid over P. And then to make it two-fold, you go up to dimension 4. You add a new vertex to make it dimension 4.
Okay, I see. So it's how many times you add
take
one
pyramid.
point to increase the dimension by 1.
Yes, exactly. And you can tell the difference because for bipyramid, you only increase the dimension by 1.
Yeah. And the one of those isn't attached to everything, so that makes sense. Okay, cool.
Thanks. Okay, and we can also define what it means by saying that a point in RD is beyond the facet of our polytope. So let's say, so this is an example in 3-dimensional. It should be obvious in 3 dimension that this point X is above the facet F. But rigorously, we say a point is beyond the facet if the supporting hyperplane of that facet is having the entire polytope on one side and the point on the other side. Okay, and after defining this, we can actually count, given a point, how many facets of P it is beyond. So here, this yellow point is above 1 facet, but if you move it a little bit, okay, that shows it's beyond 1 facet. If you move it here, then it's beyond 2 facets. Okay, we also need to define dual polytope, denoted as P star, P dual. A dual polytope is a polytope of the same dimension of P, but its face lattice is going to be upside down of the face lattice of P. In other words, the vertices of the dual polytope will be corresponding to the facets of the original polytope, and vice versa. So here, the green one and the purple one, these two polytopes are dual of each other, and we can just see quickly. Just check an example. So let's look at this vertex here. It is contained in 1, 2, 3, 4, 4 edges, and it's going to be corresponding to, for example, this facet of this green polytope, which contains 4 edges. Okay. And let me introduce the notation made by Grünbaum. So for a non-negative integer a, t superscript a is a simplex. And we can do this on an a simplex. We put a new vertex beyond exactly m number of facets. It's not gonna increase the dimension. It's still a-dimensional, and it's still simplicial. And we call this new polytope Ta sub m. Okay. And then we can apply a d minus a fold pyramid over this TA sub n, this simply show a polytope, that will increase the dimension by d minus a. So we end up with a d polytope. It's probably no longer simply show. And we call that new polytope TD comma D minus A sub M. There are many indices, but it might take like 10 minutes to get used to them. The point is that these operations behaves nicely in terms of F vectors, especially taking pyramid. You can predict exactly like what the F vector is, and I will give you a formula afterwards. But let's just see a dimension even lower example. So let's start with a two-dimensional simplex. And in order to get T2 sub 1, I want to add a new vertex beyond exactly one facet. For example, this. And then I take a convex hull. That's T2 sub 1. And if I want to go get T3 comma 1 sub 1, I need to make a one-fold pyramid, and that's easy.
Isn't the second one not simplicial though, because it's a square?
It's simplicial. Okay, that's a good question because I skipped the definition of simplicial polytope. So simplicial, a polytope is simplicial as long as all the facets are simplices. So here, yeah, it's two-dimensional. It's always simplicial.
So, but wouldn't the facet be the like square there for the second one, or?
The facets are, okay, so this polytope is two-dimensional, and therefore the facets are d minus one dimensional faces, which are just one basis.
Oh yeah, okay, of course. Yeah, that makes sense. So it's the edges that are good, so it stays simplicial.
Right, if you include the D face, the polytope itself, then by that definition, the only simplicial polytope is a simplex, right?
Yeah, I was getting confused by that too, but thanks. I guess I was thinking you could, like, if you added an edge in the middle of that that thing, but I guess that's meaningless with your definition, kind of.
Then it's a simplicial complex, but it's not a polytope.
Okay, cool.
Okay, thank you for the question. Okay, and if you actually are used to polytope languages, for example, if you know what direct sum is or what join is, then equivalently you can define these two polytopes in the following way. Just in case you're wondering, is that, yeah. Okay, I think this is the last definition. So start with, given a D polytope, we say a vertex is simple if it has exactly D neighbors, which means it's connected to exactly D other vertices. And if every vertex is simple, then we say a polytope is simple. This is just one of many definitions of simple polytopes. Here are the two other definitions, which we just call them as propositions. So if a polytope is simple, then every vertex figure is a simplex. And also simple polytopes are dual to simplicial polytope. So if P is simple, then P dual is simplicial. Okay. Okay, why do we care about those, that class of polytopes with that many indices? There are several useful lemmas made by Grünbaum. The first one says the following: start from a D simplex. Adding one vertex above exactly M facets of it is equivalent to adding one vertex above D minus M of the facets. And I'll just try to convince you with this three-dimensional example. So in order to get T3 sub 1, we start with T3 and add that orange vertex. Okay. In order to get T3 sub 2, you probably want to move that orange vertex a little bit to the right. So here, I think it's sort of above this edge. So it's above this and this facet. And you can rotate your head like this to see that they're actually the same one. Okay. Moreover, every simplicial D polytope with exactly D plus 2 vertices is one of this. So a nice corollary of lemma 1 and lemma 2 is that the total number of all simplicial D polytope with D plus 2 vertices is D over 2, right? And then lemma 3. So although the construction looks a little bit, there are 3 indices, but after those operations, you can get a relatively nice formula for the F vectors. Okay. And if you plug in A equals S and M equals 1, this will give you exactly the formula we're working on, the lower bound by Grünbaum, or phi k D plus S comma D. What this says is that this red polytope is the winner. It has the component-wise minimal F vector, right? But one can ask if there are any other polytopes satisfying this lower bound. These are just 2 examples of 3-dimensional winners. And one can ask, are there any minimizers? To answer that question, we go back to the previous proof. So if there exists some other polytope P such that Fk of P equals phi k D plus S comma D, then these 2 inequalities must hold as equalities. Okay, and we can start from the easier one, right? This box part equals 0 only for k between 1 and D minus 2, if and only if M equals 2 or S. So M equals 2, then the summation is gone. If M equals S, then the 2 binomial coefficients in the bracket are the same. And what is M? Recall from this picture, M is the number of vertices outside of our chosen facet M. And we can actually choose any facet F as long as it's not a basis. That will give us one corollary, the first corollary. It says each facet of P has D plus S minus S, or D plus S minus 1 vertices. There are only 3 choices. Okay. Now the first inequality. It holds only if this box part that we got from the key proposition is actually the sharp lower bound. So basically, the inequality from the key proposition holds as equality. Okay, so we need that this summation on the right-hand side actually counts the actual number of K faces containing some VI. And we counted, remember in the proof, we counted in the following way. And each summand is a lower bound of, each summand on the right-hand side is a lower bound of the summand on the left-hand side. So we want this to hold for every summand. And it can just I'll just briefly talk about the idea using examples. So let's say this is our P, and we can check if I pick this yellow facet as our F and label the 3 outside vertices, and try to check if this equality holds, it's going to fail immediately at V1, because the bound on the right-hand side, the binomial coefficient give us 3 choose 1, which should be 3, but actually there are 4 edges containing V1. Okay, what this says is that if this equality holds for every I, it must hold for V1, for example. Then V1 can only have D neighbors. Okay, and up to reordering, any vertex outside of this F can be V1. So every outside vertex has to be simple. That's our second corollary. So every non-apex vertex is simple. But that's probably not enough. For example, let's look at this P prime. There's one apex, the orange one, and every other vertex is simple. But we can check if equality holds for every I again. So let's say we pick this as our F. So V1, V2, V3 are here on this figure. And we can count, it's gonna fail at V3. Recall that we get this number by counting the number of K phases in a D-2 phase containing V3. But here, there's a D-1 dimensional phase containing V3, but not V1, V2. And that's why this, like, we must have been missing some phases by taking this bound. Okay. And I claim that this implies the last corollary, which says P cannot have too many facets. Actually, it can only have exactly D+2 facets. Okay, and basically, corollary 3 will just do the proof for the case of equalities for us. Because, think of it, P has D+2 facets, then P dual has exactly D+2 vertices, and we know that class pretty well. Okay, and I can briefly talk about the proof idea. Okay, I think I still have time. So, okay, so the theorem says if P is a D-polytope with D plus S vertices, and Fk of P equals Vk for some K between 1 and D-2, then there's unique choice for P. The component-wise winner is the unique winner. Okay, there's no other choice. And basically, we prove it using the 3 corollaries we just covered. So by corollary 2, I think. Yeah, so corollary 2 says every non-apex vertex is simple. Therefore, we can sort of d-pyramid P. We know that P is a possibly multifold pyramid over some simple polytope. And the polytope Q, it's simple, so its dual is simplicial, A-dimensional, with A+2 vertices. And it has to be one of those T A sub M. And by corollary 1, we know that each vertex of Q dual is in A, exactly A or A plus S minus 2 facets, and TS sub 1 is the unique polytope satisfying that condition. And hence P has to be this polytope. Okay, and that's for K between 1 and D-2. And it's in general not true for the case when K equals D-1. Okay, when K equals D-1, that means we know nothing about the middle of the F vector. We only fix the number of vertices, and we fix the number of facets to D+2. In that case, they are possibly more than one polytopes satisfying that condition. So yeah, so P can be one of these polytopes as long as A, M, and S satisfy all 3 conditions. There are special cases. For example, if S is some prime number plus 1, for example, then they'll force M to be 1, and this guy is the unique winner. But in general, it's no longer the case. Okay, that's the end of the equality cases.
All right, everybody, if you're willing to unmute and clap, or just clap with the emoji. Thank you. That was a great talk, Lei. Are there any questions out there.
Thank you.
I have a couple of questions.
Yeah.
So these lemmas of Grünbaum's that you were referring to, are those embedded somewhere in chapters 6 and 10?
Yes, from this book.
I happen to have it next to me, and I was like, is this under Polytope? And then I was like, wait, there's that notation, there's that notation. So I can find in there, which of the chapters has the description of the D-fold pyramid over the thing with the extra points? Is that in 6 and 10? I couldn't find it. I was like trying to find it, like, okay.
I think it's in chapter 6,
Okay.
section 1 and 2.
Okay.
So 6.1 and 6.2.
Okay, thank you. Then I can read all the details. And my other question is, so the equality case isn't in the paper that you put out a few months ago. Is this in a forthcoming paper you're going to do?
The equality case, I think it is in the paper. I think it's the very last section. And the proof is basically what I covered.
Oh, no,
today.
I see. There's the remark. I was just like looking through the theorems and didn't notice that it was there. Okay.
You mean the last one? Yeah.
Because once you said, look in the paper for the details, I was like, okay, I better find the paper. And then I just opened it up. Okay, cool. Thank you.
Thank you. And there's
a lot of people like the talk, and then Stefan had a question. If you want to unmute yourself and say it.
Yeah.
Well,
Okay.
Thank you for asking this question. I thought
it's good
someone
to
would
have-
ask it, so I actually
just
have
to-
extra slides for it.
But to interrupt for a second, also, like, we'll let him actually say it for the sake of the recording so that people watching can see what the question was.
Yeah, go ahead.
Okay, for the recording, I asked what about the case if S is larger than D?
Yeah. Okay, that's the question, right? Yeah, that's a natural what's next question. Unfortunately, I don't think, unfortunately, the theorem might be the last nice result that we can get. It might just fall immediately right after that. For example, if F0 is just 1 bigger, so 2D plus 1, then we have the following two candidates, I'll call. So P1 is what you get by doing the operations and then dualize, and then stack over a simplex facet. And here's a D equals 3, three-dimensional example. This is called pentasm. And from the three-dimensional picture, it's probably obvious why. And there's another candidate, P2 here. And here's why we care about these two. So the three authors of the paper from last year, I'm going to read it again. Pineda, Villavicencio, Ugon, and Yost showed in their paper that for D greater or equal to 5, then the first candidate, P1, the pentasm, is the unique winner on the edge number. It has the unique minimal edge number, which is strictly smaller than F1 of P2. But then whenever P2 exists, it will have strictly, it will be dominant on the other side of F vector, basically. It will have strictly smaller facet number. Okay, so basically since the edge number minimizes unique, the only possibility for the component-wise F vector to exist and this broke my heart. I didn't want it to like it, but what F vectors of general will actually be happening. Yeah, and I think similar things happens for 2D plus 2. I will be very, very surprised if suddenly everything is put together again after 3D. Yeah, that's all I have. Thank you.
Are there any last questions? Stop recording. Not, let's thank Le.
Thank